has been in the Angular, JavaScript, TypeScript space since 2014. Lance is an Angular Google developer expert. Lance develops Angular projects and mentors junior Angular devs on his projects. And he used to be an instructor with Angular Bootcamp. Lance is a father of two, a software developer, and a world traveler when he can sneak it in. And now he's been to Sandy, Utah, so one more for the list. And Lance's talk will be on comparing promises, observables, and signals. Please give it up and give a warm welcome to Lance Finney. Thank you.
Hello, is the mic working? Good. All right, so this is the QR code for the slides. I'll put it up at the end as well. I'll get started. As she said, we'll be comparing promises, observables, and signals. And as she said, I'm Lance Finney. I'm a software developer with a company called Inficon, and I'm a Google developer expert in Angular. So my TLDR, these are going to be a discussion of 3 different types of reactive primitives. And promises are great for single-value asynchronous reactivity. Observables are more powerful than promises because they handle and manipulate 0 to many asynchronous values. But they're sometimes overkill when all you need is a promise. Signals are the new kid on the block for synchronous reactivity, but they solve very different problems than the other 2 solve, making them a valuable new tool in your toolbox for state management. So why are we talking about all this? It's because asynchronous programming is inherently hard. It's not what we learn at first. When we're in 3rd grade and we start learning things, we learn synchronous non-reactive programming, and it's something that looks like this. All right, we're going to call A and get a result from it, and pass that into B and get a result from it, and pass that into C, et cetera, until we have a result at the end. And it's easy because it's boom, 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 boom. We know exactly what happens in what order, and we're done, and it's happy, and that is not real life. Because real life has a lot of different ways that things pop up, things that we have to respond to. And so it's things like HTTP. You make a call to the backend. Who knows how long the network lag is going to take? Or you make a WebSocket connection so that the server can send messages to you every time that stock price changes. Or who knows how long your disk access is going to take. Or how many times the user is going to type on the keyboard if they're going to type at all. Or if you're doing a game and you have to track a mouse, keeping track of every single XY. These are all things that we have to respond to because they change, and we don't know when they're going to change. And initially, all of these kind of had different APIs, which was kind of difficult to deal with. All right, this is how WebSockets work, but it's not how disk access works. What is the API we're going to need? And eventually, they all kind of settled on callbacks. And so this is a sample of a really simple callback. Let's say we have this A function, and it takes a while to do any of those things. We have a callback so that when A is done, well, we've already given it the function that it's going to use with whatever the result is that it's done, and we'll operate it. So we decide what it does when it's done, or when it's ready, and it decides what values it gives. And for a single value like this, it's not bad. But this is what we end up with. It's called callback hell. All right, yeah, we're going to make a call to A and get a result from that in that callback. And then we get that result, and we need to pass it into B, which has its own callback. And then we get that result from B and pass it into C, which has its own callback, et cetera, et cetera, et cetera. And this is often known as the pyramid of doom. It's hard to read. It's hard to reason about. Sometimes it's just hard to get it on your screen. And that's where promises come in. Promises help with that. And this is what that pyramid of doom looks like with promises. It helps us separate the call from the callback. We're still using callbacks, but they're managed better now. So we don't have that pyramid of doom. We make the call to A, and yeah, it still has a callback, but we don't give that callback directly to A. When A is done, it gives us a promise that will operate on that callback. So it gives us this promise, and we can call then on it, pass in that callback, and do what we need to do. A gives us that value of the results from A through the promise for us to use, and then we can pass it into B. And when we return a value from that, we always get another promise. And so we don't have to have this weird pyramid, we can chain them. So this dot then, this dot then, dot then, dot then, dot then. It's so much easier to just read on the screen. Additionally, we can return these things now. Maybe we want to do all the processing through C and then let our caller handle it. Well, we can return that promise and then somewhere else deals with it. We no longer have to deal with the call and the callback together. And we can make the syntax even better by using a syntactic sugar called async await. So we need to slap an async on the front. And OK, I am going to drop off the internet so that I don't keep having my messages pop up like that. Just a second. All right. So we're going to slap an async on the top. And what that means is inside it now, anytime we have a promise, we can just use the word await. And that await will then unwrap that promise for us. It's kind of like the callback, except we don't need to use a callback. And it looks a lot like that simple third grade version that we had. We still have this extra await word. We still have the async at the top. But it looks like our code. We can deal with asynchronous code as though it were synchronous code. One difference that comes up, though, is that when you do an async await on a function, you have to return a promise. This function doesn't inherently return anything, so what we return is a promise of void. You have to return a promise of something, so whatever calls this now has to deal with the promise. That's a little annoying, but overall, the code is so much easier, it's much worth it, in my opinion. And we can do error handling here. The cases I've shown so far, the A call worked. Well, what if it doesn't work? What if there's a server failure or whatever? In addition to the dot then, we have a dot catch, which is another callback where we can handle whatever error comes. And when either the then or the catch is done, we can handle the result in a finally to clean things up or just to say we're done. In the async await world, it's even nicer. We just put that await there inside of our try, and we get to use our good friends, try, catch, finally, and it just looks like normal code. We just have to do this one try, and then our catch handles errors just like any other error, and our finally does cleanup just like any other type. This syntactic sugar really helps us. And the area where promises really shine these days is in HTTP calls with an API called fetch. We can pass a URL into fetch, and it will return a promise for us. In this case, we're passing in a URL for a particular spot on the Star Wars API. And when that call is done, it gives us a promise with that response. And then we can do whatever we want. Then extract the JSON from it. Now, extracting the JSON doesn't return a promise, but we're returning that JSON. And whenever you return a promise from a promise, it gives you another promise. So now we can just chain our thens. Get our values out, do whatever the shape is of that JSON that we need, log it out, do error handling as we need to, and we get to see all the information we want about R2-D2. Just a coincidence that that was the Lego that we just had. Promises also sometimes allow us cancellation. So if the API supports it like fetch does, we can pass in an abort controller. So in addition to the URL, we can pass in a signal. Now, the last half of my talk is about signals, completely different concept. Words get overloaded, so don't get confused by that. But we can pass in a signal that it is time to abort this promise call. And in this particular case, we're going to abort it in a set timeout at the bottom. After 10 milliseconds, we're going to abort it just because 10 milliseconds is quick enough that the call hasn't finished. So it drops down to that error block, to that catch block. None of the thens get operated. We have canceled it, and we have an error to represent that we canceled it. So in summary with promises, it's asynchronous reactive programming. It's very standardized, native in all browsers. It's cancelable with the help of the abort controller, and it's ideal for single values. But what if we need to deal with multiple values? That's where observables come in. So where do they fit? I like to show this just to get an example. When we're dealing with synchronous code, if we have a single value, we put it in a variable. But if we have multiple values over space, we'll put it into an array, and then we can do things like filter and map on our arrays, and we have a lot of power there. Well, for a single value asynchronously, we have a promise, and as you might expect, that's where observables fit in. And we have a lot of the same power. We can do map and filter, and I'll explain that later. The niche for observables, WebSockets, as I mentioned before. A persistent connection that you don't know when the server is going to send you something. User input, who knows when the user is going to type. Mouse motion, who knows how often the user is going to move the mouse. Really, any event from your browser, or any stream or any combination of streams. The history of observables is that the idea was created at Microsoft in 2011 for use in .NET in a project called Reactive Extensions. It's based on the gang of four patterns of observer and iterator combined together. And it was so successful that it quickly got adopted in a whole bunch of different ecosystems, which you can see on the left. The important one for us is the second one on that list, RxJS. And it was used somewhat in our community, but it got a lot more attention when Angular adopted it for Angular 2 in 2016. And today, RxJS is the de facto standard, but it's not a true standard. A true standard is in the works. You can read the details about it here. But unfortunately, at the moment, Chrome is the only implementation of it. Maybe your team is all Chrome, and you can use it. My team isn't, so I'm not using it right now. But in the future, it'll be adopted by other browsers, and we'll all be able to use it. So how do we create an observable? A lot of ways. This is the simplest way I know of. I'll grab of from RxJS. All my examples are going to be RxJS, not native, because that's what I use. I can use this of function and pass in a single value, and I get an observable. And once I have an observable, I can do something with it by subscribing to it. So observable.subscribe, I'm going to console log, so every value that comes through, in this case it's just the one value, is going to get logged out. And then at the bottom, I'm going to log out that I'm finished. And in this case, the console log from the observable happens before the finished, because it's such a quick thing. And you might look at this and say, what's the use of this? It's essentially synchronous coding, and it's only a single value. I already talked about promises. The biggest use of this is in testing. You just want to create an observable quickly that has a single value for your test? Wrap it in an of. It's also useful in production at times, but this is not the main thing we use. I'm just trying to show a simple example first. A more realistic example comes with interval, also comes from RxJS. And now we're thinking about time. So with interval, here set to 1,000 milliseconds, it means that after 1 second, we'll get the value 0, and after another second, we'll get the value 1, and then the value 2, and on and on and on until the eventual heat death of the universe. And we can subscribe to that. And we'll see all these values, 0, 1, 2, 3, 4, 5. But notice finished, even though in the code it's at the end, it's actually the first thing that's printed out, because that's executed synchronously, and we have to wait at least a second for the first value out of our interval. But now we are handling a bunch of different values over time. We can create observables from events. Let's say we have a button on our form. We can wrap that button with from event, also from RxJS, to say I want to have an event when the click event happens. And we can subscribe to that and log out that particular event. These are 3 of many creation operators. We can also combine streams. So in this case, I'm going to create the 3 that I've already showed you, and at the bottom, I'm going to use merge to create a new stream that is the combination of those. So immediately we'll get hello, and then after 1 second we'll get 0, and then 1, and 2, and 3, and so on. And interspersed in there, whenever I click that button, will be the button events. Does this particular combination of values make any sense? No, probably not. But it's a really useful tool when you're doing something like pulling values from multiple sources that you want to bring together. I wouldn't necessarily use merge for that. I might use one of the other ones, like combine latest. There are many, many join operators that do slightly different things. But that's the power. We can combine these things, and now we operate through them all with the same API. We don't have to worry about different APIs for WebSockets and disk access. They're all the same API, and it makes a much smaller mental load for us as developers. Cancellation is built in, and it's actually really important. As I joked earlier, this observable is going to last till the heat death of the universe, or whenever I close that browser tab, whichever is first. But if I just let it go till then, it's a memory leak. When you create an observable, you need to clean it up. And the way we can clean it up is that when you subscribe to an observable, you grab a subscription object, and then you call unsubscribe on it. So in this case, we're going to have our interval. After 1 second, we'll have a 0. After 2 seconds, we'll have a 1. And after 2.5 seconds, we're going to unsubscribe. So we only get those 2 values, and then the observable is done. There are many other ways to unsubscribe, but this is the most explicit and direct. But just being able to handle streams doesn't really mean anything if we can't manipulate them. And there are many operators for that. I'm just going to show a couple that are a lot like what I mentioned earlier for arrays. So we're going to start with our interval, 0, 1, 2, 3, 4, 5, 6, 7, whatever. I'm going to pipe on that the filter operator. And that says the only values that come through are the values that are less than 6. So we'll get 0, 1, 2, 3, 4, 5. And then the observable will still be sending the rest of those. We haven't unsubscribed from it, but we're just suppressing them. We're filtering only to see the ones we care about. And then after that, we can map. And what map will do for us is it'll take each value that comes in and replace it with whatever is the calculation. In this case, it's going to square each value that comes out. So 0, 1, 2, 3, 4, 5 becomes 0, 1, 4, 9, 16, 25. And that's what we see here. And an important thing to note is that the order matters. If I swapped the order of these two, we would square first. 0, 1, 4, 9. Oh, wait, 9 doesn't match the filter anymore. We would only get the first 3 values out. With the order we have here, we get 6 values. So the order that you put things in your RxJS pipelines matters. And a note, if you're using native observables, it doesn't use pipe. They get chained after each other. So dot filter dot map. So some differences in the APIs. The most important and often the most confusing, well, not the most important, but important but often confusing operators are called the higher order operators. So let's imagine that we wanted to do something where we're going to emit our 1, 2, 3, 0, 1, 2, 3, 4, 5. But every 4.5 seconds, we want to start over. So we want to get 0, 1, 2, 3, then 0, 1, 2, 3, 0, 1, 2, 3. And in a way we can do that is have an outer observable, that is the interval, 4.5 seconds. And then an inner interval, that is the 1 second. And if you hear what I described as what we want, this might be what you'd start with because, hey, this map is going to replace those original values with the new set of numbers. Isn't that what we want? And it actually isn't. Because what interval returns is the observable itself, not the values in the observable. So if you just use map, you're going to get the wrong values. And a lot of people will see this and say, OK, then I'll do a subscription within a subscription. And anytime you see nested subscriptions, you probably are in the wrong spot and you want to use a higher order operator instead. What we need is something that will flatten those inner observables to give us the values that are in those inner observables. And merge map will do that for us. So instead of map, it's now merge map. And merge map will grab the values out of each of those inner observables and put them on the screen. And does that give us what we want? Not exactly. Yes, we get 0, 1, 2, 3, and then we start back at 0, but we also still get the old values. So it's 0, 1, 2, 3, 4, 0, 5, 1, 6. They're interspersed, and eventually at the end we're at 6, 11, 2. That's because we're not canceling the old set of numbers each time we get a new set. And there are times that merge map is exactly what you want, but that's not what I said I wanted in this case. So in order to get what I said I want, we use switch map. So what switch map will do, it also unwraps things like merge map, but additionally, it will clean up for ourselves as we switch from one to the other. So we start out with 0, 1, 2, 3, and after 4.5 seconds, we create a new one, and we start 0, 1, 2, 3, but we've canceled the previous one and switched to the new one. And after the next 4.5 seconds, we cancel that one, and we switch to a new one. 0, 1, 2, 3, we cancel and switch, on and on and on. And this is probably confusing if this is the first time you've seen this. I know that I'm giving a very high-level introduction to it. This talk here was a talk at an Angular convention several years ago that I highly recommend if you want to see more on this. It's actually a 20-minute humorous sketch about switch map. Okay? But it works, and it's a really good explanation. So I recommend that if my explanation was just too quick. But overall, I've talked about a bunch of operators, but there's a lot more. These operators are the power, but often also the confusion of RxJS and why people get overwhelmed with RxJS. There are dozens, actually over 100 operators, which can get overwhelming. Fortunately, there are a lot of resources out there to help you learn them. Whether you learn well from text descriptions or you've learned well from visual depictions of marbles moving around, there are different tools out there to help. There's also a link here for a tool that I call the Choose Your Own Adventure. It's a path where you can say, all right, I know I want an operator that will take two different operators and combine them in this way and then cancel it in this way, and you follow through question after question until you get to a leaf in a tree, and you say, all right, that's the one you want. All of these are really good tools. But another thing is, don't get disheartened by being overwhelmed initially, because you don't need to learn them all. I really like this article on the bottom that posits 7 specific operators that if you start with those, it'll solve like 90% of your problems by combining them in various ways. Often there'll be another specific detailed operator that would have done things in 1 line instead of 5, but you can get most of the things done with this. Look at a basic list of operators first, understand those both, or understand that small list, and then build from there. So in summary, they are also asynchronous reactive programming, handle 0 to many values. They're cancelable, which is important to do. If you create an observable, you need to cancel it, otherwise you have memory leaks, and there are some operators that do that for you as well. Not as standardized as promises, but they're working on it. And you might think RxJS is feeling threatened by this standardization, but they're actually thrilled. If you read this post here, they don't want to be in the observable business. They want to be in the operator business. They want to be a Lodash for events. And I didn't really talk much about native versus RxJS. If you want to learn more about that, I recommend this video by my fellow Angular GDE, Rainer Hanekamp. He goes into a lot of detail on that. Now it's time for signals. So what are signals? They're things that hold a value and notify consumers when the values change. I think of it as a box that has a value. But it's not just that. That box knows the other things that are paying attention to that box and knows how to tell them, hey, I've changed, you're going to have to change too. And it's a simple concept, but it's surprising how much power we get out of that. So where do they fit in this matrix? Like, it feels like all the boxes are filled in, and they are. It's actually the wrong question to ask where they fit in, because it's a different thing. Signals solve a different problem. The main problem they solve is helping frameworks figure out how to keep your DOM, your visual representation, up to date with your actual state. And to understand this, it's useful to step back to gaming program by analogy. When gaming programming first started, they used immediate mode, which meant, all right, we have our screen, and there's a little change, like our little figure moved from here to here. All right, now we need to redraw the entire screen. And that worked. It was easy for the developer, but users hated it because it was slow. We're spending a lot of time and energy redrawing things that hadn't changed. We're spending bits sending information across the wire that hadn't changed. So next they added something called retained mode that would say, all right, we're only changing this 5% of what's on the screen, so let's just redraw that. But that meant a lot more work for us as developers to figure out what's the 5% that changed, and how do we keep track of that? So much better for the users, but harder for us as the developer. The goal with signals is that we'll get immediate mode behavior for the developers with retained mode performance for the users. So here's a simple example that I'll come back to later that is just a calculation that doesn't need signals yet. Let's imagine we're trying to schedule a room for our conference, and so we know there's going to be 50 people, all right? We've declared that first, and there's going to be a cost per guest, but there's a discount if you have a lot of people. So if we had more than 60 people, there'd be a discount. Well, we only have 50, so the cost per guest is going to be 30 bucks. Figure out our total cost by multiplying the two together. We get our value of 1,500. That's great. That's easy. We're back to boom, 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 third grader math. Great. But reactive programming, like asynchronous programming, is hard. Sure, we have these things done, but then we change it. And, actually, we need 100 guests, not 50. And if this is in a function, yeah, we could call this again. But let's think about it at a higher level. If we don't have just a function that we're calling, how do we know that we need to recalculate cost per guest in total just because num guests changed? What's the relationship there? And more tricky, how do we know what order to recalculate these things? We could just recalculate total. Oh, num guests changed. Let's recalculate our total. We'll keep our cost per guest, and so we're going to get 3,000, and that's the wrong number because it's not taking into account our discount. And so some systems will do that, and they'll calculate that first, and then they'll realize, oh wait, cost per guest changed, and then they'll recalculate, and we'll see the wrong value for just a blip on the screen until the right value comes in, and our users are annoyed by what we call a glitch. We want to avoid that. We want to be able to figure out what calculations need to happen. And an analogy, this is something that we actually see quite a bit already. We see programs that do this for us with spreadsheets. And I'm not claiming that Excel is implemented with signals, but it's a useful analogy, at least for me. Because each of these cells in here is like that little box I talked about. And here, number of guests and cost per guest are independent values at the top, and total cost is calculated from those, and there's intermediate calculations along the way that these all interact. But when you use a spreadsheet like this, you've probably seen if you change the independent variables, the value at the bottom changes immediately without a glitch. That's what we're going for. That's what we get with signals. And a lot of frameworks have ended up in this basic direction. So I'm not going to talk about all of these, but a whole bunch of them have come here through what's essentially convergent evolution. It's kind of like with crabs. If you look at this picture and you say, oh yeah, those are all crabs, they probably all have a pretty recent common ancestor, but it's not true. These had different ancestral forms that all evolved to the same design because it turns out that pinchers and 6 little legs are really efficient for scurrying on the bottom of the ocean. So they've convergently evolved to that. And that has happened with a whole bunch of these frameworks. A notable absence is React. That's evolving in a completely different direction. But a lot of these are evolving together. I'm going to talk about the history of a few of them. Knockout, about 10 years ago, got really close. They had a lot of the pieces together, and then in 2014, they got the last piece to be really, really close to figuring out all this stuff. But they didn't quite have glitch-free operation, and so they needed to calculate their values multiple times in order to clean up glitches. But it was a lot closer than what anyone else had done. And then in 2015, MobX got it right with glitch-free operation using push dirtiness and pull value. I'll explain what that means later. And a dependency tracking to know what order to do the calculations. It got it right. But the first framework that really pulled it all together under the name signals was something called Solid.js from 2021. And you might never have heard of it because Solid.js is just created by this guy named Ryan Carniato. Smart guy. He actually wrote this blog post that goes into a lot more of this history if you want to read it. But there's so many JavaScript frameworks, and just another one created by some guy, people don't notice. But what people notice is one of the big ones, adopts it. And Angular isn't as big as React, but it's big enough that when it adopted Signals a couple years ago, the ecosystem took notice. And you might wonder what this other symbol is. It's called Wiz. It's an internal framework at Google. So Angular they use that a lot, and they share it with the rest of the world. Wiz is what they use internally for the really, really high performance applications like Gmail and Maps and YouTube. And lately, the two frameworks are converging. They have the same signal implementation, which means when you use YouTube, you're using the same signals that Angular developers use. But since there was this convergent evolution, there's a need for standardization. It is really early in the process. It's only at stage 1. But it is there, and interestingly, they're using the Angular Wiz implementation as their default reference implementation at the beginning. And you can see more details about the process on this video. So once we have this going, how is this going to help us solve that problem that I talked about earlier? This is some kind of pseudocode-ish based on the reference implementation. We're going to do the same things as before, but we're not just going to have a simple number of 50. We're going to wrap it in a signal. We're going to wrap it in a box that knows how to communicate with things that depend on it. And then instead of just calculating cost per guest, we'll have a computed signal that explicitly depends on the other signal. So when num guests changes, it will get recalculated, and it will get the value from num guests, and it'll get that 50 out and say 50 is less than 60, so our number is 30, and that's the value it's going to have in its box. And then our total will be a computed, wrapping around callbacks. Callbacks didn't go away. They're just managed better now. We're going to wrap this callback that gets the values out of both num guess and cost per guess so that we can multiply this together. And then effect is this other thing that is actually going to call it and say, I need to get that value out of the total. And so it's going to get that value, and it's going to do the product, and we'll get our result. But then we change it to num guess to 100. And this is where signals actually matter. What happens when we change that value in that box is that num guess has a new value. Great, it's done. But it notifies the things that depend on it that they are dirty. So now cost per guess knows that it's dirty, and total knows that it's dirty. They know that they have stale information. And since they're stale, I thought I killed that. All right. Since they're stale, it tells the effect that it needs to recalculate. So effect is going to ask the total for its new value, and then total is going to say, all right, I need to recalculate. In order for me to recalculate, I need to get the numbers from num guess and cost per guess. Num guess isn't dirty, but cost per guess is dirty. Cost per guess, you calculate yourself. All right, thank you, give me the value. Now I can report it to the screen. And that's what I was talking about earlier with pushing dirty and pulling value. When we make a change to an independent value, it pushes dirtiness to everything that depends on it, and then when something wants to see the value, then it recalculates. And we get a calculation once as necessary and no glitches. So what does the syntax look like? It really depends. So here's some examples, TC39, proposal, Angular, et cetera. They all have slightly different looks. All of them make sense, but they're slightly different approaches because they have different history and conversion evolution. Similar with setting. Every single one of these makes sense. I might write it any of these, just an equality to set the value, or set count, or dot set. All of these make sense. With the computed, these are all different ways of doing callbacks that are wrapped, except interestingly for solid, it's so signal specific you don't even need to wrap it in anything. But they're all just wrapping callbacks in computed. And when we want to get the value, there's multiple ways to do it. Dot get, or just put parentheses around it, or after it, or get the value out. And the point is, the different ecosystems have come up with different ways to do it. So when we standardize, is there any worry that we're all going to have to do it now the Angular way or something like that? And the answer is no, because the goal of that standardization team is that they are writing the core implementation, and then the frameworks will decide what we as end developers work with. So you're not going to be forced to do the Angular way when Preact starts using similar techniques, things like that. We will all get to use what we're already comfortable with. And individual frameworks will provide more APIs as well. Like that effect thing, that's not going to be part of the standardization, at least not yet. But your framework will give you that. So here's an example from my world, Angular. It's a simple component to represent a clubhouse. So for this clubhouse, if there's a door, and if the door is open, we show a welcome message, and if it's not, you don't see it, and there's a button that has an appropriate message of either close or open the door, and you click the button and it closes or opens the door. The only independent state on this is the door open. We create that by saying signal of true, and that gives us a writable signal. So on that first line of the template, we're going to get that value out of the box with parentheses and then show the welcome message. And then the button text is computed. So it's going to go in there and say, get the value out of the door open, and we're going to say close door in this case, and put that on the screen. But then the user clicks the button, and that will call toggle door. And this could use set, like what I showed an example before, but Angular also has another thing of update where it uses another callback that gives a previous value, which is great for a toggle. We just invert it and put it back in. And this is where the magic starts to happen. When we make that change, the door open has changed. And now that will automatically tell the template that that line of the template is dirty. It will also tell button text that it's dirty, which means that button text will tell its line of the template that it's dirty. And now Angular knows that those specific lines of the template are dirty, and so it will ask those specific lines to recalculate, to re-render those specific lines. Not the whole app, not even the whole component, but those specific lines. And so we'll say, recalculate these things. Dirty has been pushed down. We're now going to pull the value, and we can put those on the screen. And I want to say some of this, like awesomeness of performance, doesn't quite exist yet, but it's what they're working towards. So how do signals improve the developer experience? No risk of memory leaks like we have with subscriptions. One-way data flow. Memoization, it caches the value, so once you've calculated it, you don't need to calculate it again. And glitch-free operation. So now that I've talked about these, which one should we use? You both it. We use them all because they have different goals. As Ben Lesh, who's the head of the RxJS team, says, use signals for state, observables for events. It's pretty simple, and the opposite is silly and bad. And this is actually why, part of the reason that Redux gets a lot of flack in places. Observables are not really intended for state, but with Redux, they figured out a way to shoehorn it in, but that really wasn't a good fit. Signals are the fit for that. Divide your labor. Use your observables or promises for your events, and use your signals for your state management, glitch-free one-way data flow, binding to your templates. So part of your application is going to use one, part of it's going to use the other. What's the gap? Your framework's going to have different ways. I'm an Angular guy, so I'll show you the Angular way. It has interoperability APIs to convert observables to signals and signals to observables, which makes life easy. So we have things like this. Imagine we have an application where we want to show the details of a book. There's a list of books, and when you click on a specific one, we take that ID as a signal, make a call to the back end to get all of those details to put those on the screen. So we start with a signal, but we have to convert that to an observable because that call to the back end, signals can't do that. They can't wait for network lag. So we have to convert that to an observable, so the observable can do that switch map and all that back-end calculation stuff. And when it's done, we can convert that to a signal and then put that on the screen. Now, this game of going back and forth gets kind of ungainly, so Angular has created what they call the resource API to help us out with a lot of this. So again, we can start with that signal, but within this resource, Rx resource, we'll pass that in, and that means that every time that signal gets a new value, it's going to get passed into the stream, which is going to call to the backend and do all the switch mappy backend stuff that we need. And then at the end, it's going to give us a signal. But it's not just that signal. The resource API has a signal on what the value is If there's an error, it has a signal for that. It has signals for, is it loading now? Has it loaded? All the call state stuff you want. Has a reload option. So it's this powerful state management tool that helps you deal with the front end as signals and the back end let observables do what they're good at. But even though I talked about observables being the back end, remember that promises still have a niche. I'm showing this again because, yes, arrays are more powerful than variables, but that doesn't mean we wrap every single variable we find in an array. That's just shooting ourselves in the foot. And similarly, with asynchronous, we'd want to remember that even though observables are more powerful than promises, promises still have a place. And specifically, it's for fetch. So in summary, promises and observables are both asynchronous, signals are synchronous, no concept of time. Promises have a single value, observables are 0 to many, signals 1 value at a time. Promises are totally native, observables are getting there, signals are further away. Promises can sometimes be canceled. Observables, it's important to do and it's built in, and signals, it doesn't really, you don't need to do it really. The only real utility for promises is async await. For observables, there's so much power from RxJS, and signals, that's going to depend on your implementation. And they each have their niche. HTTP for promises, events for observables, and reactive state for signals. And I hope that helps you understand how to use these three primitives. Thank you.